so I'm just going to show them the video. Okay, so lab 21, we are building a traffic signal controller. Okay, so much like I did with lab 19, lab 9 when we did the perfect pencil machine, the easiest way to try to understand what's going on in lab 21 is to actually not just look at the lab, but try to figure out what you're doing. So what you're trying to do in lab 19 is build a traffic light controlling system that has a bit of intelligence to it. So it looks after something like a main street, which in this case we'll call baseline, and a side street, which in this case we'll call Navajo. So this is where the Max Milk is, and the Minto's over here, and the McDonald's is over here, and there's some other building over there. So what they do is, there's two ways you can run this intersection, right? You can have the lights that go on a particular cycle and have it run over that cycle all the time. But the problem is, since baseline is a main street and gets a lot of traffic compared to what Navajo gets, at 3 o'clock in the morning, if there's cars on baseline but there's no cars on Navajo, it doesn't make any sense to continually go through the cycle of the lights. So what they do is they have some logic in there and they have some sensors in there that determine if there's cars coming up on the side street. So probably at 2 o'clock in the morning, if no car ever shows up on Navajo, baseline will be green all night, right? Because there's no need to shut down traffic when there's nothing going the other direction. So you'll know that this is happening if you've ever been on an intersection like this and you're driving and before you get to the intersection you see the hand start flashing to let you know the light's going to change, and then out of nowhere it just goes right back to the walk signal. That's what happened. So there's logic in there. The logic has determined that there's no vehicle coming in on the side street, so there's no need to change the light. So the light will stay green. Now normally, and you can usually see this, but you'll see a little cut line in the pavement, and it usually extends a little beyond the stop line because they know that nobody stops right at the stop line. Everybody goes a little further. So there's actually a loop of wire in there that acts as an inductor or something, and then the purpose of that loop is to sense when there's a vehicle at that intersection, okay? So that's one of the parameters that what we're going to look at, and it's one of the ones we're going to look at in this lab. The three parameters we have to look at are the timer long. That's 25 seconds, that's the green light timer. So in baseline, when the light turns green, in this example, it stays green 25 seconds, okay? It could stay longer if there's no vehicles. So the 25 seconds for the main street is a minimum. So the light's always going to be on at least 25 seconds. On the side street, it depends if there's sensors on here. So that 25 seconds is a maximum. So the light could be 25 seconds, but it could be a lot less than that if there's only one car. And we'll talk about the logic and how you make that happen in a moment. The only one that doesn't have to do anything with anything else is the timer short. So the short timer is 4 seconds, that's for the yellow light. It never changes. It doesn't matter if there's traffic, no traffic, middle of the day, middle of the night. When the short timer comes on, that's for the yellow light, and whenever a yellow light comes on, it's on for 4 seconds, and then it changes to red. Nothing affects that. The last parameter is VS, which is your vehicle sensor. So that just determines if there's a vehicle on the sensor, because that's going to make a difference in the logic that we're using. Okay? So the first diagram that you see in Lab 21 is this bubble diagram. So this is a state diagram. We've started to look at state diagrams with counters already. So this is for the 4 states, because there's only 3, right? There's only 4. So when the main is green, the side is red, and then the main eventually is going to turn yellow. The side's still going to be red, and then the main is going to be red, and the side's going to be green, and then eventually the side's going to go to yellow. The main will stay red, and then you're going to go. So these are the states, and they go through in that order. they again use a gray code. So the first state is going to be 0, 0, then 0, 1, and then 1, 1, and then 1, 0. The problem is the system that's checking to the sensors and the timers and everything goes fairly rapidly. So that means in every state, you always have two choices. You can stay in the state you're in or go to the next one. You can stay in the state you're in or go to the next one. You can stay in the state you're in, go to the next one, stay in the state you're in, or go to the next one. So for example, when you hit this state, when the main light turns yellow, there's going to be a loop checking that countdown timer, right? You guys kind of do similar things to this in PLCs or whatever. Do you guys do PLCs yet?
No.
Never mind, but probably in micros.
Yeah.
If you haven't done it already, you will do that in micros. So basically, the countdown timer starts, the 4-second timer starts counting down, and then there's something checking. Is the timer still active? Yes. Okay, I stay in the current state. Is the timer still active? Yes, I stay in the current state. Is the timer still active? Yes, I stay in the current state. Is the timer still active? No. Go to the next state. Okay, and that's how it checks. Because we have to design this to do it automatically, because obviously there's not some guy standing there in a little box watching the traffic and running the lights. So it all has to be automated. So some of these states are easier than others. So for example, the timer short, the short timer, if the timer's true, which means if that still evaluates to 1 or true, then you stay in that state, and then as soon as the timer is not true, then you go to the next state, right? So the timer starts, as long as that countdown timer is still going, you stay in the current state. As soon as that timer expires, you go to the next state. Okay, so now we have to try to figure out, other than the short timer is easy because it doesn't depend on anything else. But to stay in the main state, you have TL or VS not. So what that means in English is if baseline is green, so if your main street is green, what conditions do you need to be true for baseline to stay green?
No,
right?
on the side.
One is the timer has to be active. So as long as that counter is still counting down from 25 seconds to 0, then you have to stay in the current state. But how we make this a minimum is we have an OR and we take not the vehicle sensor. Right? Because if there's no vehicle on the sensor, then VS is 0, right? But that means VS not then will be 1. So if there's no vehicle on the sensor, then this is true, right? So if the timer's, because we know that 1 or anything is going to be 1. So if any of those or either of those is 1, then the output's going to be 1. So if my timer is still counting, then this is going to be 1, and I'm going to stay in the current state, right? If there's no vehicle on the sensor, VS not will be 1, which means this will be 1, which means, again, this is going to equal to 1, and I'm going to stay in the current state. So that's how you stay in the current state all night, right? So the first 25 seconds is guaranteed, and then after that, it's up to the vehicle sensor. So if there's no vehicle on the sensor for an hour, the light on baseline will stay green for an hour, right? The only way to change it is if a car rolls up on that sensor. So when you look at the table, they do it a different way because your first state is 0, 0. So the timers always have to be counting and always have to be doing something. So you can't just tell a timer to stay in the state you're in. So the way they do that is they just program the next state to be the same as the state you're in, right? So that means, that's why this table looks like this. So you have 0, 0. If you want to stay in the current state, you just make sure your next state is also 0, 0. If you want to go to the next state, then you're going to be going to 0, 1. Right? So one of those doesn't really matter, right? Because if you're going to 0, 0 or 0, 1, right? this is going to be 0 regardless. So when you look at your table, I want to make sure I'm using the same order in the book. Okay, so this is basically your Q1 and your Q0. So the Q1s and the Q0s go to the DS1s and the DS0s. So what you're going to hook up to here, either way, is a 0, so you can just put a 0 here. This one's pre-filled in the table, but that's why that's there. So whether I go to state 0, 0 or 0, 1, that first bit is always going to be 0, right? So I don't have to worry about that. Now this, I have to worry about. We did something similar to this when we did the, no, earlier than that, when we did the multiplexer used as a comparator, and you had the B1s and the not B1s and that kind of stuff. It's a similar exercise. So in the box before that, they give you the two choices to hook up to DS1. One is the TL or VS naught, and the other one is TL naught and VS. Now, it's not obvious from that, but you'll notice that whatever keeps you in a certain state, if you have that, you stay in the current state. If you don't have that, you go to the next state. So what makes you go to the next state is always the naught of this. So this is actually the naught of this, but it doesn't look like it because they did the De Morgan equivalent. So if you have TL or VS naught, the naught of that looks like this. So the De Morgan equivalent of that would be break the line and change the sign. These are two, so they disappear. So what makes you go to the next state is TL naught and VS. But that's really the naught of this. So in the earlier lab I mentioned we had the chance of taking B1 or not B1 when you were going to the input. So now you have to figure out whether you want TL or VS naught, or you want not TL or VS naught, which is this. So then now what you have to do is look at the relationship. So when TL or VS naught equals 1, you need this to be 0, right? When TL or VS naught equals 0, you need this to be a 1, because when it equals to the 0, you're going to the next state, so this has to be 1. So when this is 1, this has to be 0. When this is 0, this has to be 1. So that's an inverse relationship. So you're not going to take this, you're going to take the naught of that, which is this. So in this box, you'll have TL naught VS. Now when you see that table in the lab, that's already filled in for you, but I'm just going through it so you can see how I got that. So the next one, now you're in state 0, 1. So again, to stay in the current state, the next state is the same as the previous one, and you can go to 1, 1. So here again, whether I go to 0, 1 or 1, 1, the Q0 is always going to be 1, so that's why there's a 1 in that box. And I think that's the end of the pre-filled ones. So now what you put here is either going to be TS or TS naught. So what goes here? So now you have to look at TS and what you need Q1 to be. So when TS is 1, you're going to stay in that state. And to stay in that state, this has to be a 0. So when TS is 1, this has to be 0. When TS is 0, this has to be 1. Right? So when T1 is 1, Q has to be 0. And when TS is 0, the Q has to be 1. So that's an inverse relationship again. So that means that you're going to pick TS naught. Okay, so for the third state, now you're in 1, 1. So you're either going to go to 1, 1, which means you're staying in the current state, or you're going to go to 1, 0, which is going to the next state. And the choices here are TLVS or TL not or VS not. Now again, not horribly obvious, but this is the not of this. It's just the De Morgan equivalent again. So if I take TL VS not, I break the line, change the sign, so I have TL not or VS not. So this is the not of this. So again here, my Q1 is going to be 1 regardless. And here, when TLVS is 1, I need this to be 1. When TLVS is 0, I need this to be 0. Right? So when TLVS is 1, I need this to be 1. And then when TLVS is 0, I need this to be 0. Is that an inverse relationship or a direct relationship? It's a direct relationship, right? If this is 1, I need to keep this 1 so that I stay in that state. If this ever goes to 0, I need to go to the next state, so that's 0. So that's a direct relationship. So I'm going to choose this again, and that's going to be TLVS. Now, the other one again, you're on one of the yellow light states, so the choices are TS and TS not. And again, if TS is 1, I need this to be 1. If TS is 0, I need this to be 0, right? Because this is 0 regardless, so I don't have to worry about that. So when TS is 1, I want to stay in this state. This state is 1, 0. So when TS is 1, I need this to be 1. And then when TS is 0, I need this to be 0. Is that an inverse relationship or a direct relationship?
Direct.
It's direct again, so that means I'm using TS here. So this is going to be 1. Wait, did I do that already? Yes, I did. Oh, sorry, that's for the next one. So again, the Q, this one's going to be 0 regardless. So when you're hooking up the multiplexer, it just goes to ground. And this input, when TS is 1, I need this to be 1. When TS is 0, I need this to be 0. That's a direct relationship, so I'm going to use the TS. So that's what goes in that table and why. Now, if you look at the circuit, what can I remove here? I kind of need this, so I'm going to remove it. So the circuit is 2 multiplexers, 2 D flip-flops, now I'm not going to draw the clocks and the presets and clears, so you know what those are supposed to be. So this is the Q1, this is Q0. So the Y output goes to this D, the Y output goes to this D. Now, the Q1s and Q0s go to the selects. Hopefully you all remember how multiplexers work. So you can see that everything controls everything else, right? Because what you put on the multiplexer is going to control what's on the Ds, which is going to control what's on the Qs, which is going to control which input of the multiplexer goes out. So in the first state, C0, I need 0 and TLVS. So C0 on the top one goes to ground, and C0 on the first one goes to TL naught VS. Now how does that work to stay in the loop? Right? So if this evaluates to 1, which means if my timer is still going, or if there's no vehicles on the sensor, this stays in the current state, which means this is 0. So what I do is I take the naught of this, which is TL naught and VS, remember, because we had an inverse relationship. So that goes to C0. So if I'm staying in the current state, that means TL is 1. So that means TL naught will be a 0. So there's a 0 on that NAND gate. So what's the output of that NAND gate going to be? 0. This is 0 because it's grounded. So that means my outputs are 0 and 0. That means I have two inputs of 0, 0 on the D, which means what's going to be on the Qs when I clock it?
0.
D flip-flop just takes whatever's on the D and puts it on the Q. So if I clock this, that means my Qs are both going to be 0. That means both of these are going to be 0. And if you have 0, 0 on the select, it selects C0. Right? So the two zeros will give you C0. As long as the countdown's still going, this is going to be 0, this is going to be 0, which means 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 it's going to select C0 and give you two more zeros. That's how it stays in that loop. Okay? So eventually the timer will expire, so this will be at 1, but if there's no vehicle on the sensor, this is still going to be a 0. So that's how baseline stays green all night, right? 0, 0 goes to the Ds, goes to the Qs, goes to the selects, goes to C0, which gives you two zeros, and then it stays in that loop. The only way to break that is if the timer expires, and then eventually some car shows up on the sensor. So now this will be a 1, which means this will be a 1, which means this will be a 1. So when you clock it, you're going to be 0, 1. So you're in the next state. And the next state is going to take the green light that was on baseline and turn it yellow and keep the other one red. Remember you did the traffic light earlier, like lab 13 or something? If you actually hook up the output of this lab to your lab 13, then you'll get the whole system, because then you'll actually see the traffic lights going. Okay? Now, the problem is when this goes to 0, 1, that changes my selects now to 0, 1. So now C1 is selected. So what do I need on C1? That's my next state. So we know that DS, this is DS1. So we know DS0 has to be high. So it goes straight to plus 5 volts. So this is DS0. So we know that C1 has to go high, so we're just going to put this to plus 5 volts. And then what are we putting on C1? TS naught. Now how you stay in that loop there is, once you get here, you start your 4-second timer. Okay? So, when you start your 4-second timer, TS is going to be 1, which means TS naught is going to be 0. So you're going to put a 0 out here. This is always going to be a 1 because it's plus 5 volts. So 0, 1 is going to give you 0, 1, which is going to give you C1, which is going to give you 0, 1, which is going to give you 0, 1, which is going to give you 0, 1, which is going to give you C1, and you're going to stay in that loop. Now, eventually what's going to happen is this countdown timer is going to run out. So as soon as it runs out, TS will be 0, but TS naught will be 1. So then this is going to go to 1, this is going to go to 1, this is going to go to 1. Right? So now you're going to go to the next state. So now the main red and the side is green. So now, but the thing is, and this is, if you're going to make a mistake, this is where you're going to make it on this lap, because 1, 1 is actually C3. Right? You're not going in order. It's a gray code. You're going 0, 0, 0, 1, 1, 1, 1, 0. So in order on the multiplexer, you're going C0, C1, C3, and then C2. Okay? So what do you put on C3 then? Right? This is C3, right? Because you're going 0, 0, 0, 1, 1, 1, 1, 0. So C3 is here. So that means you have to put a 1 on DS1. And what else do you have to put on CS3 then? TLVS. They actually give you a hint here because even though they don't tell you what goes here, they put an AND gate. So if they put an AND gate, then it's not going to be TL naught or VS naught. It's going to be TLVS because they have an AND gate there. So that's what you do. So how you stay in 1, 1 is as long as your timer's still going and as long as there's still cars on the sensor, then this is going to be 1. This is 1 because it's always 1. You're going to have 2 1s on the Ds, 2 1s on the Qs, 2 1s on the select, which is going to give you C3, which is going to give you 1, 1 on the outputs, and that's how you stay in that loop. So the reason they switched to the De Morgan equivalent here for not TLVS is this is a little easier to understand, right? Because if the timer expires, or if there's no vehicles on the sensor, you go to the next thing. So this is how you make the green light here. This is how you make the green light here a minimum of 25 seconds. Because when that light turns green, it will be green for 25 seconds, but if the vehicle leaves the sensor, then if 5 seconds after the light turns green, the vehicle leaves the sensor and this becomes a 0, then this is going to go to 0. Which makes sense, because if this light's on for 25 seconds, and there's traffic here, but there's only one car, as soon as this light turns green, if there's only one car, he leaves right away. What's the point of leaving the green light on another 20 seconds when there's no cars there? Right? So obviously this system gives preference to the main street, right? When the light turns green on baseline, right, it stays green for a minimum of 25 seconds. But when it turns green on Navajo, it's a maximum of 25 seconds. Because if there's only one car, as soon as that couple seconds after that car leaves, the light turns yellow. So then, if the timer expires, the reason you want both of these on an AND is, let's say that there's an endless supply of vehicles here. Right? Let's say after one of my lectures, 10,000 people show up and then they all leave one at a time and go up Navajo. Then there'd be cars on the sensor for an hour. Well, you can't have that light on the side street be green for an hour. So, and if there's a long lineup of vehicles, when the timer expires, the timer will kill it, right? If there's an endless supply of vehicles on the sensor, as soon as that 25-second timer is done, you're done. And the light changes yellow. So if either one of these happens, right? If either one of these goes low, you're going to go to the next state. So that means this will go to 0, this will go to 0, this will go to 0, this will go to 0. So now you're going to be 1, 0, and now you're going to be on C2. Right, so what do you put on C2? Right, DS1 is going to get TS. And the other one's going to get 0, so ground. So again, as long as TS is 1, this is going to be 1, this is going to be 0 because it's all ground. And as long as that timer is 1, this is going to stay 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 1, so you're still going to stay on C2, and again, it just loops, right? It's kind of a really clever loop, this circuit. But then as soon as this timer expires, as soon as TS expires, it goes to 0, which means this 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 goes to 0, and 0. And then you're back on state, the first state again. So now the first state will depend on the timer and the vehicle sensor and the 0. And you go through the entire loop that way. And then everything starts again. And that is lab 21.